Good morning. Once again, I welcome you to this lecture on soil mechanics and geotechnical engineering. And I will start now exactly where I have stopped in my last class or last lecture. And I was discussing about the determination of coefficient of consolidation by laboratory method, and that actually we have there are two well known methods are available, and one is given by Taylor's method. Taylor's sometimes called root 2 method, root T method, and another is Kashagande's method, that is actually log of time method. And this root T method, before going to root T method, what was observed, that root of time factor versus degree of consolidation plotted and observed certain behavior, and when it is the laboratory data, consolidation data, root time versus dial gauge reading is plotted, the behavior was similar. So, based on that observation, there is a method proposed to find out the point corresponding to 90% consolidation, and once you know the point corresponding to 90% consolidation, then you can find out T90, that is time required to complete the 90% of consolidation. And once you know the T90, that is small t, the time for 90% consolidation, and also we generally know time factor 90% T90 actually time factor for 90% degree of saturation, that is from the relationship we can find out. So, T90 if you once find that is known, and T90 again equal to CV into T90 by h square, where actually T90 is obtaining from the curve, that is time required for completing the 90% consolidation, and h is the thickness of the sample, and that depends of course, whether it is double drainage or single drainage, how much to be h, that I have explained, I will explain again. So, h also known, and time 90% consolidation time also known, h is known, only unknown is CV. So, equating this one can find out the value of CV. Similar to that, there is another method that is called log time method. It was proposed by Kashaghande, and this method similar to that, similar to the root T method. This method also initially time factors, actually log time factor versus degree of consolidation was plotted, and experimental data also plotted in the same manner, that means log T versus dial gauge reading or sample thickness, and behavior was similar. So, based on that similarity, there actually the method is proposed to find out time required for 50% consolidation. 0 and 100 is located, and then finally, in between 50% point is located, which is average, considered to be average, and time required for 50% consolidation, if it is determined from the test, and time factor for 90% degree of 50% degree of consolidation, one can find out from the relationship, and then these two to be equated. There also similarly, we have the only unknown is CV, because thickness and time required for 50% consolidation is also known. So, that CV, based on that comparison or equation from that relationship, one can find out the CV. So, now I will go step by step how to do this, how to use this experimental data for determining the coefficient of consolidation CV. So, before going to that step by step procedure, I will just show the theoretical curve, that is root time factor versus log time factor versus degree of consolidation, and the laboratory plot, that is root time versus dial gauge reading. These two plot I will show first, and what are the observation made first, and then I will go step by step procedure what you have to do actually when you have the experimental data on consolidation. So, I will skip initially 2-3 slide and then again come back. So, this is the plot, actually two plots are shown here. one, this is actually theoretical plot. This is the theoretical plot. You can see u versus log T v. T v is nothing but time factor. Sometimes we use v, sometimes we do not use v. So, this since it is a vertical compression you are talking about. So, T v is used. So, this is the plot, it is parabolic and then it is going this side, and this is the plot when it is time versus consolidation or time versus dial gauge reading. Dial gauge reading means what? When the soil is compressive, dial gauge indicate how much settlement or consolidation took place. So, that dial gauge reading is taken and time is noted, then log time versus dial gauge reading. So, this is plotted and this shape and this shape almost similar. So, because of that, and if you have this, and then actually we can this parabolic part actually will have a standard way of variation. So, because of that procedure is to find out from this curve, you have to find out 0 consolidation point and 100% consolidation point. And this is actually after 100% consolidation, whatever that is actually secondary consolidation, and secondary consolidation of course, we will not discuss right now. This is a separately I will discuss later on, but so before start of secondary consolidation, that means end of primary consolidation. So, how to locate that? You can see that this part this is the there is a point of inflection that will change, and then here actually it will become towards end it will become straight this side. So, what you have to do? You have to extend the straight portion backward, and from this there is a point of inflection. From there actually you have a straight line and extend, then it will meet at a point that is here, suppose at this point. So, this point actually indicates the end of primary consolidation. So, that means 100% consolidation. So, this is actually a 100, and that means 100% compression, this is suppose, and then to find out 0 compression. So, what you have to do? We can choose 2 points. This is the parabolic portion of the initial parabolic portion of the curve. We can choose 2 points in such a way that T 2 equal to 4 times T 1. This is the way you have to take, and then if you take this, then the distance or ordinate between A and B, suppose some value, then from A we will select another point, suppose C say here, and locate that point, and through that point make a horizontal and intersect this ordinate, at that point indicates actually 0 consolidation. So, we get 0 and we get 100. So, that means from here to here this is actually the consolidation settlement. So, this rate may not be uniform, but so if I take at 50%, we are supposed to get the average. So, because of that what we do, between this and this we will find out the midpoint of it, and from there I will project on this curve, and that will give you the, this is suppose A 50, then this will give you corresponding T 50. So, like a Taylor's method, what you have tried to find out? We tried to find out time required for 90% consolidation, that is T 90, and in Casagrande method, that is by log time method, what we are trying to find out? We are trying to find out T 50, that means time required to complete 50% consolidation. So, this is the point. So, the outcome of this plot is ultimately determination of T 50. So, this is the by and large the curve or how to plot, and there are different steps, but now I will go back to the original slide the first right from beginning, and try to show you the procedure how you have to follow to find out the CV. You can see that coefficient of consolidation by log time method. So, similarity between log t versus u curve and sample thickness versus log time log t is observed, and we have shown already. Hence, the sample thickness versus log plot log t plot. Actually, log t plot can be utilized to determine the coefficient of consolidation. So, since their similarity is there, so that can be what similarity. So, two things: determination of thickness corresponding to 100% consolidation to be determined first. The intersection formed by the final straight line produced backward, which I have shown already. Toward this side I will produce back, and the tangent to the curve at point of inflection is accepted as the 100% primary consolidation. So, already I have shown. Once again I will show that. So, the curve is coming like this. So, I will produce back this one, and I will something like this, and I will produce this one, this intersecting point, and this will be your A 100. I will go back to the figure again, and the dial reading designated as R 100 or A 100, R reading 100 or A 100. So, in figure it is A, but this is written as. So, do not get confused, they are same. So, this is actually once you got the 100% consolidation point, next thing to determine of the thickness corresponding to 0% primary consolidation. So, in this actually what you have to do, select 2 points on the initial parabolic portion of the curve in such a way that time are in the ratio of 1:4. That means, T 1 or T 2 will be 4 times T 1. This is the way you have to choose. The difference in thickness between these 2 points is then equal to the difference between the first point and the dial reading corresponding to 0 primary consolidation. So, this is the observation. If Z is the ordinate difference between A and B, a point C will be chosen at Z above point B or point A actually as per figure, intersecting the horizontal through point C to dial reading axis gives the point corresponding to 0 primary consolidation. So, I have shown already 0 at the top. Suppose it was like this, this curve was something like that, one point is here, another point is here, and then I will get the distance between this. So, from here actually same distance point I will locate here and draw a horizontal, then these give you a 0. So, I will show again. So, this is the way you locate the point corresponding to 0% consolidation. Next is the interval between 0 and 100% consolidation is divided into equal intervals of percent consolidation. So, suppose I have 0 here and 100 here. So, I will uniformly distribute. So, if I want to find out 50%, it will be just exactly at the midpoint. Since it has been found the laboratory and the theoretical curve have better correspondence at the central portion, that means, at the average the value of CV is computed by taking the time t and time factor t at 50% consolidation time t. So, that means, I will find out T 50 and I will from the curve I will find out small t 50. So, these two. So, T 50 from the relationship between t versus u, that means, T 50 means what? Time factor corresponding to 50% degree of consolidation, that is actually we will get, and that value will be 0.197 most likely, no 0.48. So, this is actually, so if I do not know the value, then I can write T 50 equal to C V T 50 by h square. So, ultimately C V is unknown, because this can be obtained from the relationship h actually thickness length of the drainage path, and if it is single drainage it is equal to the thickness, and if it is a thickness of the sample, and if it is a double drainage then half the thickness of the sample, and T 50 to be obtained from the graph. So, this is the way one can find out the CV. Once again we are coming back to this curve, you can see same thing as I have mentioned, that you have produced this back and you have produced tangent here, the intersecting point here A 0, and you have chosen a point here and here. then between these distance is z, then I will draw one point above this z. So, that point suppose C, and then draw an horizontal passing through this intersecting this, that is A 0, and this is A 100. So, A 50 will be midpoint of that, from there we will get the T 50, this is will give you T 50 from here. So, that finally will equate to get the coefficient of consolidation. Now, if two layers of the same clay soil is same, but with different drainage condition, and so drainage path H 1 and H 2 are acted upon by the same pressure increase and reach the same degree of consolidation in terms of T 1 and T 2. So, drainage path is different, thickness of the layer is different, but soil is same, but again degree of consolidation is same. So, obviously, time will not be same. So, T 1 and T 2 suppose respect, then theoretically how will be the relationship? Suppose T 1 will be C V 1 suppose layer 1, T 1 time required for time for the layer 1 and H 1 square. So, drainage path suppose one layer is something like this, single drainage, and this is suppose H 1, another layer is something like this, and this is double drainage, and this is suppose H 2. Okay. So, so that is the thing, but since soil is same, though initially I am writing C V 1 and C V 2 separately, but since the soil is same, coefficient of consolidation will be same. So, ultimately this one, so T 1 and T 2 time factor, since for both cases we achieve some same degree of consolidation, that means U 1 and equal to U 2, then T 1 will be equal to T 2. So, if T 1 equal to T 2, then ultimately you will have C V 1 T 1 divided by H 1 square equal to C V 2 T 2 divided by H 2 square. So, see, we both the cases we achieved the same degree of consolidation, then your corresponding to T 1 and T 2 they are equal. So, T 1 or T 2 also will be equal. So, if they are equal, then these two can be equated, and once again you can see, since it is same soil, the C V 1 equal to C V 2. So, ultimately what is left? T 1 by H 1 square equal to T 2 by H 2 square. So, from for a particular soil, when laboratory test is conducted on a particular thickness, and if it is asked to find out the actual characteristic, the thickness is this much, what will be the time to be time required. So, directly one can use this relationship to find out the timing. So, this is another observation or important information which can be used in solving the problem. Now, I am almost at the end of compressibility topic, but once again what I will do, I will summarize the important points what I have discussed so far, and then how to utilize that using by applying to the different problems. In 2-3 lectures actually I will devote to solving the problem, mainly because there are different types of problem possible, and different exam different types of problem come. So, all varieties of problem I will try one after one, maybe 2 to 3 module I will take on solving problem addressing different aspect of the compressibility of soil. So, this is the summary what we have done. Actually, you can see first we have defined coefficient of volume compressibility. Sorry, this is not this is the coefficient of compressibility, actually not volume. Volume compressibility will come later on. This is not the coefficient of compressibility. coefficient of compressibility is A, sometimes we write A v, either way it can be written. So, this is d by dp and it is nothing but slope of E versus P curve. So, E versus P curve if you plot, it comes like this. So, if you select 2 points, sorry, it will not come like this. So, if you select 2 points, then from these 2 points we can find out the slope between these 2 points, and that is nothing but d by dp, and you can see unit will be it will be meter square per kilonewton, because E does not have void ratio does not have any unit and dp is below. So, inverse of pressure unit will be the coefficient of compressibility. And another term we have defined mv, coefficient of volume compressibility, which is nothing but A v by 1 plus E. That means, unit will not change, only coefficient of compressibility divided by original volume. So, that is then it become coefficient of volume compressibility. A unit will be same, meter square per kilonewton, and mv different ways it can be expressed. mv also A v by 1 plus E, that is also can be expressed dH by H 1 by 1 by dp. So, change of volume volume compressibility over unit pressure. So, from that definition if you use dH by H 1, where H 1 is the original thickness and dp is the pressure change. So, if I simplify, it become 1 by H 1 dH by dp. So, this is another way of defining mv, volume compressibility. So, if you know the directly thickness versus pressure or pressure versus thickness change, from there also we can find out dH dp like dE dp and then divide by original thickness, that also give you volume coefficient of volume compressibility. Once you know the coefficient of volume compressibility, one can find out the total settlement, and that is shown here rho c total consolidation. This is actually nothing but total consolidation settlement, and this is actually mv into dp into h, and you can see it was meter square per kilonewton. So, dp kilonewton square meter. So, it get cancelled, ultimately the entire unit of this entire thing will be a unit of h. So, we supposed to get settlement in meter or millimeter. So, that is things are coming. So, mv dp into h, this is the relationship. When you use the mv method for finding out the consolidation, this is the simple formula. So, how to do that? If there is a layer here and you have to find out the E versus P curve, and from there we can get A v, and then A v by 1 plus E will get m v, and how to find out d p. If this is a layer and you have applied load here, then what is the pressure increase in the middle of the clay layer, that is del p, that can be obtained by either by Bose or by trapezoidal distribution like this, one can find out, and then finally multiplied by thickness, that gives you the total consolidation settlement by mv method. Next thing is we have considered another is another important thing, many times will be useful, d by 1 plus, this is the volume compressibility and coefficient of volume compressibility, change on volume over original volume in fact, and this is also change of volume over original volume, considering one dimensional consolidation. If we consider the consolidation is one dimensional, that means there is no other change in the lateral dimension, only compression because of the compression in the vertical direction, then this relationship valid. And another definition of void ratio, if I know the soil volume is V and then cross sectional area is not changing. So, if I think that idealize that thickness of the solid is H s, then and total thickness is H, then I can define void ratio H minus H s by H s. This is the way sometimes solving some problem, this is important and required. Another thing we discussed that E versus P curve is a curve, but when you plot E versus log P, it becomes a straight line, and mostly straight line. There will be some observation, obviously initial portion that I have discussed. One second, I do not want to discuss again. Only thing what I want to mention, that the major portion of the E versus log P curve will be straight line, and the slope of the straight line will be C c, compression index, and that C c equation will be E 1 minus E 2 by log P 2 by P 1. So, if it is a something like this, your curve is like this, and this is P 1, then this is P 2, then this is E 1 and this is E 2, and this is P 1 and this is P 2, then and this is in a log scale. Then your expression for compression index is E 1 minus E 2 by log P 2 by P 1, and then if you know the C c, then we can find out the consolidation by compression index method by using this formula C c into H by 1 plus E log P 2 by P 1, and this is actually, this formula is applicable only for normally consolidated soil, and when it is a over consolidated soil, that will be treatment will be little different, and that is also I have discussed, but I will once again summarize. That is one. So, again your we have defined in general actually P 1 and P 2 in mathematically, but when you talk about soil mechanics, then P 1 is nothing, sorry, P 1 in the soil mechanics, actually when you apply P 1 is nothing but sigma naught dash, which is that actually it is the effective overburden pressure before application of the load. So, P 1 is nothing but sigma naught, and P 2 equal to sigma naught dash plus delta sigma dash. So, that is the way it is mentioned. So, the two cases will be sigma naught plus delta sigma when less than pre consolidation pressure, then this is the formula to be used, where instead of C c, CR will be used, and CR if it is not given, it is 1/3 to 1/5 of C c can be taken, and sigma naught plus delta sigma, if it is a greater than sigma P c, that means if the curve is something like this, and you have applied initial is here and del sigma is here. If this is the del sigma, then sigma naught plus del sigma is greater than sigma P c. So, this is the case when you are here. In that case, it will have two parts, from here to here one part and here to here another part. So, CR part is this and CC part this, these two together will be the total consolidation settlement. This is again I have repeated, I have explained before. So, once again repeated here. Then determination of time factor, this is the well known formula for time factor CVT by H square, and this is can be related with U when it is less than 60%. This is the formula can be used for finding out T, and if U is greater than 60%, this is the formula can be used for determining U. And then degree of consolidation is the consolidation attained at time t divided by total expected consolidation settlement, and Cv is the coefficient of consolidation, and H is the half the thickness of the layer for double drainage condition and thickness of the layer for the single drainage condition. So, all those things I have explained before. Once again I am giving summary here. And for determination of Cv, the two methods, actually root time method and log time method. Root time method we get T 90, this is T 90 we get, and once you get T 90, then Cv can be related to Tv. T 50 actually is nothing but 0.48, sorry T 90, T 90 actually 0.48, and so this is the way I can put T 90 and then we can get the value. And when it is a log time method, we get T 50, and T 50 corresponding to T 50 is 0.197. So, that value if I use, then Cv can be related to this, and from there one can find out the Cv. So, both way Cv can be obtained. Thank you. with this I will stop this one. Next one I will try to show some application, different theories whatever I have discussed. I will try to explain one by one the application. Thank you.